Next up, we're going to have Kostas I can never say your last name, Kostas, I'm sorry. Kostas is from the Foundation for Research and Technology in Crete, postdoc with John Vontas' group out there. And his main research focuses on molecular diagnostics of insecticide resistance, and he's going to talk us through that.
Thank you, Mike. Good morning. So, during the last decade, we have seen striking resistance phenotypes to start to arise, both in agricultural pests and in major disease vectors. For example, in the Tetranithus urticae agricultural pest, there has been a phenotype which has developed a 1600-fold resistance to the insecticide abamectin. But also in Africa, in the Anopheles gambiae vector, there have been some multi-resistant populations that are resistant to all registered classes of insecticides. So the question is, why does this happen? And the answer is not that easy to give, because there are multifactorial patterns of resistance that are dependent on target site resistance, on P450's overexpression, and ABC transporter gene overexpression. Two of the most studied, well-studied examples are the ACE1 mutation in the target site the mutation target site of ACE1 gene that confers resistance to organophosphates and carbamates, and the overexpression of CYP6P3 in the Anopheles gambiae vector that confers resistance to pyrethroids. Our group was able to identify a single mutation in the hidden synthase gene that confers up to 50,000-fold resistance to diflobenzuron. We were able to validate this data in vivo using a CRISPR-Cas9 system, and unfortunately this mutation was also found in Culex pipiens mosquitoes, which are the prime vector of West Nile virus. So, molecular analysis of resistance can provide valuable markers for diagnostics that can be assessed via various and very dissimilar methodologies, ranging from microarrays to rapid diagnostic tests and PCR. Regarding Anopheles gambiae, these protocols have mostly been developed for target site mutations, which can be accurately defined using PCR-RFLP, allele-specific PCR, and of course Tachman qPCR assays. So these protocols are very dissimilar. They require sophisticated platforms, and also, as mentioned previously, the markers for metabolic resistance, which are RNA markers, are lacking and can only be assessed via microarrays, which is very difficult to perform and very difficult to explain methodology. And also the cost is very high. So what should we do? Shall we stick with bioassays? It is true that both discriminating dose bioassays and quantitative CDC bioassays are very close to operationally relevant data, and they give very useful information regarding resistance. But on the other hand, there are many disadvantages because bioassays require a great number of mosquitoes. They cannot detect cross-resistance. The sensitivity is quite low because resistance is detected only at the late stage. And of course, the mechanism of resistance cannot be known based solely on bioassay data. So, maybe we should not stick with only with bioassays, because molecular diagnostics are highly complementary tools to support and substantially improve evidence-based IRM. And I'll give you two very clear examples for that. The first comes from a P450 that we were able to identify, which is CYP6CM1, that confers resistance to the white flies. And this specific P450 is responsible for resistance in the neonicotinoid imidacloprid, but at the same time has nothing to do with resistance to another neonicotinoid, which is acetamiprid. Concurrently, this specific P450 gives resistance to pyriproxyfen, which belongs to a completely different mode of action. So the spectrum, the catalytic spectrum of P450s is not always predictable. As I mentioned previously, a single mutation in the hidden synthase gene gives a striking resistance phenotype to diflobenzuron in Culex pipiens mosquitoes, and this phenotype requires 100 times the recommended dose. These mosquitoes require 100 times the recommended dose to be killed. So we did a wide monitoring via bioassays in Culex pipiens populations, and these bioassays show full susceptibility in two different regions. So the question is, can we go only with bioassays in this case? Data from molecular diagnostics show that after screening these two populations for the presence of the resistant allele, this resistant allele was found only in one region, and of course at a lower frequency and at a heterozygous stage, which gave a very minor phenotype which could not be detected at any case via the bioassays. So my point is that bioassays and molecular diagnostics can be highly complementary and not necessarily exclusive, mutually exclusive tools, which should both be used in order to support evidence-based IRM. So the next question is, how do we do these molecular diagnostics? How do we practically perform them? Well, the traditional approach so far was to genotype individual mosquitoes, large numbers of individual mosquitoes, and come up with a frequency for each allele, may that be KDR West, KDR East, or ACE1. We propose that this approach can be done in mosquito pools in order to save both resources and time. And why is this? This is because the final information that we give to applications like IR Mapper is a simple allele frequency that can be safely be extracted from mosquito pools. And we have proven that by developing regression models, polynomial regression models that transform a simple CT value that you get from analyzing a mosquito pool from a qPCR machine into allele frequency. We have developed this model in training sets, and we use different validation sets to validate this data, and the difference between expected frequency and observed frequency, the mean error is quite low, is 3.5%, and also the level of detection is quite low, it's 5%, which means that you can detect a heterozygous mosquito out of 9 wild type in a pool of 10 mosquitoes. So why not analyze let's say 20 pools of 10 mosquitoes instead of analyzing 100 mosquitoes individually and save 1/10 of the cost. Talking about mosquito pools, gene expression assays have traditionally been performed in mosquito pools either with microarrays or with singleplex qPCR. We wanted to simplify this process further, so we developed multiplex, tripleplex Tachman assays for a panel of major detoxification genes like CYP6P3, CYP6M2, CYP9K1, P4, CYP6Z1, and GST2, and we validated these Tachman assay panels, and we saw that the information that we get is equally reliable to singleplex qPCR or microarrays. You get the same fold change by doing either method. Of course, we wanted to develop a method also to detect plasmodium in mosquito pools. So we detected the dissection-free method, which does not require the dissection of mosquito heads, based on the expression of genes at the mRNA level, which are expressed only at the infectious stage. So all these molecular diagnostics are freely available via a Horizon 2020 project, which is called InfraVec 2, and you can check it online. You can apply for this. It's available free of charge for researchers that do not have access to molecular diagnostics. And this service is available for two main disease vectors, Anopheles gambiae and Aedes aegypti. We also want to, as a next step, to integrate all these molecular diagnostics, all these assays to a simple sample-to-answer platform in order to monitor the infectious status, the insecticide resistance profile, and other traits of mosquito pools. So I will show you a quick video how this automated platform works. The whole extraction process of nucleic acids, reverse transcription, and qPCR takes place in this very simple machine. You just have to load the sample into the platform, which is a small disk. I have a prototype. I can show you more details if you want. So you add the sample, and then the sample is lysed, and nucleic acids are bound to magnetic beads, which are transferred from one wash chamber to another in order to wash the nucleic acids, and finally to get the clear eluate, which has both DNA and RNA. So after that, the eluate is transferred automatically to a chamber where the polymerase is in place and is aliquoted after that to the reaction chambers where the qPCR takes place, and you have the rehydration of specific reagents, meaning Tachman probes and qPCR primers. So after that, you get some very nice and very standard qPCR amplification curve, which is the fluorescence versus cycle number. And at the end, you have a simple output, which are only the CT values. And this is how the fluorescence is detected in the platform. So we aim to develop. We are in the process of developing two separate lab disks, one for malaria vectors and one for arbovirus vectors. The expected features are these lab disks should be usable with mosquito pools, should be used under basic and difficult, let's say, laboratory conditions. Only a small equipment is required, which is quite not expensive, let's say. No hazardous chemicals are required. And of course, at the end, the whole process of reporting the data comes with an automated computer-based documentation. We also want to integrate the data from the lab disk into the data management tool, the DTMS, which has been developed by LSTM, by Mike and Marilise Coleman, and also to communicate all this research and all these outputs via a communication tool, a serious game. This is done through the framework of the DMC Malbec project funded by the European Union. So a special thanks to all the partners that contributed to this project, and of course I have to acknowledge the funding from the European Union via two large projects, which are DMC Malbec and InfraVec 2. And thank you also for your attention.
Okay, so we have enough time for some questions. If anybody has, come to the microphones and state your name and where you're from as well, please. No burning questions at the moment. Okay, we're going to take questions at the end as well.
Yeah.
So thank you.
Thank you.
And we'll have you back to